We just came up with the derivative of tan x. We just figured out that d by dx of tan x is equal to sec squared of x. So now let's do some examples just to kind of practice using that rule. So let's say y equals, I don't know, let's go with e to the x times tan x. Weird function, no idea what it looks like. So what rule are we going to have to use here? Well, we've got e to the x times tan x, right, times, so that should tell us product rule. So product rule, derivative of the first, times leave the second, plus leave the first, times the derivative of the second. There you go, that's the derivative. Maybe we'll factor out the e to the x, which was common, so tan x plus sec squared x. But that's good. So that's the derivative. Let's try another one. Let's say f at x equals, I don't know, tan of, let's say tan of sine. So what rule do we have here? We've got the chain rule, right? We have an inside function and an outside function. Sine is inside tan. So we have to use the chain rule. So chain rule tells us it's the derivative of the outside, which in this case would be sec squared. So the derivative of the outside at the inside, so at sine x, times the derivative of the inside, which in this case is cos x. So that's it. The derivative of tan of sine x is equal to sec squared of sine x times cos x. Alright, so let's try another one. So we did a chain rule, let's do a quotient rule. So let's try cos x plus 1 over, I don't know, tan x. Okay, so quotient rule. So g prime at x equals the derivative of the top, which is sine x, times leave the bottom, which is tan x, plus leave the top, cos x plus 1, times derivative of the bottom, which is sec squared of x, all over tan squared x. Okay, so that's the derivative. Now what you're often going to do is simplify with trig derivatives. So if this is messy, you might be able to simplify things. Like for example, tan x I know is equal to sine over cos x. Right, that's tan x. Plus, and okay, so cos x plus 1. And sec squared is 1 over cos squared x. That's all over tan squared x. I can move this down a bit. Ooh, I can. Okay, so that's sine squared x over cos x plus, now if I multiply this, I'd have 1 over cos plus 1 over cos squared x all over tan squared x. So we can move down a bit more, very little bit more. And then maybe just get a common denominator. Nah, I don't even know. Okay, so we'll put a cos squared on the bottom. So tan squared x cos squared x. So I got a cos squared on the bottom. So I'm going to have sine squared x times cos x, because I need to get that over one more cos, plus cos x plus 1. I guess that's a little bit simpler. And actually, cos squared times tan squared. I'm just going to have to say this. I don't have any more room to write it. Tan squared is equal to sine squared over cos squared. So those would cancel. So you'd have sine squared x cos x. Oh no. Plus cos x plus 1. Did I get that in? All over. And then that was just equal to sine squared on the bottom. And, I mean, that's pretty simple. That didn't simplify too much, but sometimes things will cancel out a lot better. But, usually that's just what you do. You simplify using trig identities. Let's see if I can come up with one where it's actually necessary. Alright, here's a good one. So let's say y equals, let's go with tan x times sine x? No, times cos x. No, times tan x. What did I say? Times sine x. Times sine x. Tan x times sine x. Is that what I had? I don't know. So we want to get the derivative of this, so product rule. Derivative of tan is sec squared x times derivative of sine x plus leave tan times the derivative of sine x, which is just cos x. And you might say, oh, okay, I can leave it like that, but now notice tan x, if I write it, well, even this too, right? Sec squared is 1 over cos squared times sine x plus sine x over cos x times cos x. So that really helped over here, right? Coses cancel. And even over here, you have sine over cos squared, so you could just do sine over one of the coses is tan x. But then you still have the 1 over cos. So I can multiply that by a sec. Plus, and then there's just sine x. So you might say, okay, why did I do that? Like, what's the point? Well, maybe sometimes you would want to get the second derivative. So if you want to get the second derivative of this, it's way easier to do the derivative of this than it was of this. Actually, probably best not to write that as sec. Let's just write it as cos. So you got to do the quotient rule on this one, but you know the derivative of this and this, and you got to do the derivative of sine. That's easy. That's just cos. I'm not going to do this one, but hopefully you can see that's a lot easier to figure out the derivative of this than that original thing. So that's why sometimes you want to simplify. Okay, we'll do one more example. See if I can get it in under. Okay, so here's the example we'll do. We're going to find the points where this function tan squared x has a horizontal tangent. So remember, horizontal tangent means the slope of the tangent is 0 or the derivative is 0. So we want to get the derivative of this. Remember, that's equal to tan x all squared. So that means we've got to use our quotient rule, or not, chain rule. So the outside function here is the squared. So 2 comes down. Tan x times the power of just 1, because the power drops by 1, times the derivative of the inside, which is 1 over cos squared x. Well, actually, you know what? You probably would want to write it as sec squared x, because that's how we frame the rule, right? The derivative of tan is sec squared x. I knew that I'm going to set that equal to 0, and if I want to solve this, I probably want to change sec squared to 1 over cos squared. The reason I can do that, well, if you remember how to do trig equations, you want everything to be in the same, kind of trig function. So I'm going to change tan to sine over cos. That's not squared, I don't know what I'm doing. Times 1 over cos squared, which is equal to 2 sine x all over cos cubed x. So we want to know when this is equal to 0. Well, it's just equal to 0 when the top is equal to 0. So 0 equals sine x. So when does sine x equal 0? There's a lot of places, right? At 0, at pi, at 2 pi, at all the negative directions of this. So basically any multiple of pi. Actually, dot dot dot, because there's etc. If we want to write that in a formula, we could say n times pi, where n is just any integer, right? If n was 1, then it would be pi. If n was 2, it would be 2 pi. If n was negative 1, it would be negative pi. So all these values, you're going to get a horizontal tangent.